Mic on. Okay. Let's see how it goes this time. I got some new cool overlays. And there's no music this time. Honestly, I don't know if people watching the stream prefer having music or no music. Probably no music is better, so they can put the one they like. Hope the font is big enough. There's a chat overlay, which I don't know. Let's see how it goes. Anyways, last time I went through the GADT's exercises, which were the first chapter of this very interesting repository by I am Tom. And today I'll work on the second chapter, which is on flexible instances. So now that we are experts in GADTs, today's module will be a very short rationale for flexible instances and where we need them. Okay, so we already used them in the first chapter's exercises, but they weren't really explained. Just the compiler asking us to enable them, and I did so. Anyways, here is a really underwhelming class with no functions or goodies. It has one parameter a, and that's it. Okay. Now it comes as no surprise that we can write an instance for any type you can imagine, of course. If you uncomment the last one, you'll see that GHC gate gets upset. Does it? Yeah. Use type synonym instances if you want to disable this. Okay. Specifically, it's upset because we are writing an instance for string, but string is a type synonym for a list of chars. However, it has a solution to suggest to us type synonym instances. The extension lets us write instances for type synonyms, which is nice, which GHG can then expand for us, meaning that our instance for string will be expanded to char, list of char. Problem solved, right? Well, not quite. Okay, remove the extension, which I didn't add. Anyways, we command that instance. Now let's imagine we get up and wrote an instance for char. Okay. And it's still complaining. This time asks for flexible instances. So if you uncomment this line, you'll see that the error we saw with string once we enabled type synonym instances. Although now the error says char, list of char instead of string. Let's take a look. Okay. This is actually one of GHC's most helpful extension errors. What this says is that our instances must all be for types which it calls T. If those types have type parameters, all the parameters must be variables. None of them can be concrete values. Okay. And all of them must be different. Interesting. So obviously char, so this could be thought as list of chars, and char is not how do you say, it's not a variable, it's a concrete type, so this is not working without flexible instances. So below are a few examples that work. Notice that they're all some type constructor applied to a number of variables. So some class list of A's works. Either EA works because there are two different variables. I think this won't work, right? Yeah. This doesn't work. because the type variables have to be all different from each other. And this one has no variable, of course. Conversely, here are some that don't work. This may be typed as a parameter that isn't a variable, which bool is a concrete type and it's not a variable. This one has, have two of the same variables. Okay. The variables are unique, but one of either's parameters isn't a variable. Maybe A is a type that contains a variable, which fails GHC's check. It has to be a type variable with no exceptions. So if we uncomment this, I guess we'll get, again, the compiler complaining. Yes. And ask us to enable flexible instances. Okay, interesting. That literally is it. The flexible instances extension lifts these restrictions for us. We can now use type synonyms. We can write instances that enforce equality between types. Okay, such as writing an instance for either EE. And we can specify arguments to types that aren't type variables. In other words, we can write instances for types with other types in their parameters. Okay, so it's like this example here, where the second parameter is not a variable, but it's another concrete type which contains a variable. Okay, this one looks pretty easy and clear. Let's check the exercises. Okay. Class pop quits A. Okay. Which of the following instances require flexible instances? Don't cheat. This is a tricky one, but look out for nested concrete types. Okay. Guess how I'll go. I will uncomment the ones that don't need flexible instances, and hopefully I don't get any compiler error. So here we have a bool, which is a concrete type. So this one should be fine. Yes. Here we have a type which contains another concrete type, so this one should be fine too. There are no variables and no synonyms. Oh no. Why? I already made a mistake. Of course. Yeah, I'm so stupid. This is one of the first things that he told us. Type variables need to be variables and not concrete types, so this one doesn't work, but this one works. Okay, so this one is a tuple with two variables which are different from each other, so it should be fine. Yes. Here we have a list containing a tuple which is not a variable, but it's a concrete type. So this one should be an error. Well, let's check just to be sure. Yes, okay. And this one, the type constructor containing a variable, so it should be fine. Is it? Yes. Yes, yes, yes. Okay. Well, just one mistake for 6 lines. I guess it's good. Okay, this one looks trickier. So we have a new type, Rio, RA, which is the Rio of a function from R to I of A. Remember, this is a new type. Okay. And then we have a type synonym. Okay. Which is the Rio with the quote. Instance pop quits Rio int A. I think this one doesn't work because we have a concrete type instead of a variable, which is the int, right? Yeah, okay, got this right. This one should work. Yes, because we have two type variables. This one should give us an error because we are using a type synonym, and this is not allowed without flexible instances, or actually without that other instance, which I don't remember the name of. Yes, okay, doing great so far. Pop quits. Huh. I think this one gives us an error, right? Because we have a concrete type inside, which is not allowed. This one should be an error. Yes, okay. So I think this one can be written as a function which takes an R and takes an IO of A. And obviously here we have a concrete type, which is IO, and is not allowed without flexible instances. Instance pop quits. This one is fine because we have a function from A to B, which are two type variables. Yes. Okay, what about this? This is tricky. So this one is a function that goes from A to a function that goes from B to C. So we have a nested concrete type, and I think this doesn't allow us to write this instance without flexible instances, right? Yes. Yes. Okay. Then we have this instance pop quits. I'm actually not sure of how Haskell handles these three tuples. I mean, is it to be either this, which is fine, or could it be something like A, B, C, which is not fine? I have no idea. It works. So I guess the constructor is actually this one with the three commas. Kinda cheated here. This one doesn't work. Pretty sure this one doesn't work. Yeah, we get an error. It's fine. Oops. Come on. This one should be fine. And this one is an error because we have two of the same type of variables. We have A and A. Let's check it, but I'm pretty sure this will be an error. Yes. Okay. And then we have the last one. So we have a data pair A, which is a pair of AA, and then a type synonym. Okay. Oh, this is tricky. Okay, this one is an error for sure. Yes. And I think this one is fine, and it's a way to show us how to handle this, because we are only a one type variable. And I think GHC won't care that much that we are using it twice then in our type constructor. Let's see if I'm right. Yes. And this one is an error because we are defining an instance for a type synonym. Okay, I did it. There's no viewer yet, so probably no questions. I think this was pretty self-explanatory, simplish. Definitely much more simple than the JDT one, luckily. Okay, let's check KindSignatures. Should get more exciting here. It's taking a long time. This virtual machine is a little slow. Okay, module 3, in which our heroes discover KindSignatures and the ways in which they can help us. We'll see where we need them and where they're just good documentation. Interesting. We are hopefully familiar with the notion of types. Tree is a value of type int. Nothing is a value of maybe. IO string, okay, and so on. However, there is also a notion of types for types, which is kinds. Yes. In our standard everyday usage, all the types you use have the same kind. Star, which we pronounce type. I think star is deprecated right now, so yeah, it's better to use type. In fact, we can use type instead of star by using the following import. Import data kind. Okay. Okay, yeah, this is a good habit to adopt as star is going to be deprecated soon in favor of the more explicit and hopefully clear type. Now we know all sorts of things of kind type. What does it mean? Now we know all sorts of things of kind type. Okay. Class of kind type A. Yeah, this two need flexible instances to compile, which is already enabled here. I'm not entirely sure what's happening. I mean, what's the point of this? Let's go on. We can start with intuition that the type kind is inhabited by things with a runtime value. This isn't 100% accurate, but gives us somewhere to start. All our values have a type that is a kind of type with a capital T. We can see, for example, that maybe int is of kind type. Yes. Maybe is a funny one though, right? We could think of it as a type level function. So yeah, maybe it goes from type to type. In other words, maybe on its own isn't a type, it's a type constructor. A maybe of what? The type checker asks. Maybe int is a type, and maybe unit is a type, but maybe isn't. We can say that maybe as kind function from type to type, because it's like a function that, given a type, gives us a type. For example, given int, we get maybe int. Given bool, we get maybe bool, and so on. Yes. It is because of this that we can write the following instance. Instance of kind type maybe. Okay, yeah, and we get this kind of error, which is something that maybe it's getting it's familiar when you're trying to write instances for a functor or a monad, then you get this kind of error. The big problem here is that in the absence of a better idea, GHC will assume that the type class parameter is of kind type. How do we tell it otherwise? We provide a kind signature. This is exactly what the extension exists to do. Okay. So here it's creating a new class. I can split the window to show the old one. So the old one was just had a as a type variable. The new one has a, which has its own kind signature, which tells us that it's a function from type to type. Here we say that the kind of the argument to this class must be a type to type argument. Of course, we actually know plenty of things with kind type even if we haven't thought about it before. So maybe list, either e, kind of either is type to type to type. So it's type, is it either or either? I don't know, always get it wrong. Type. Okay. Try deleting the kind signature from the of kind type to type class and see that we end up with kind errors for every instance above. Yes. We'll see later on when we discuss constraint kinds and data kinds that this is one of the extensions we'll turn on every time we want to do something a little complex. I also think it's a nice one simply for the sake of documentation. Class, my favorite befunctor, which takes an element that goes from type to type to type. Okay. Makes sense. So right now we can think of all our kinds as being type or from A to B for some kinds A and B, and that's it. However, there's one more that is worth mentioning, constraint. This is the kind of constraints, of course. So we have a class OA, which takes a constraint of kind constraint, and then we can pass it, eq int or show string. The last one may look a bit odd. Isn't unit a type? Shouldn't JHC complain that type and constraint are different kinds? Well, in true Haskell fashion, unit is actually overloaded. In the constraint kind, it refers to the empty constraint, a constraint that is always true. The tuple syntax is actually that unusual when we think about it. Yeah. We use it to define multiple constraints, so like here. So we have show A, AQA. Constraint is the kind of every member on the left side of the fat arrow. Sometimes we just have a single constraint. Sometimes we have several. In order to have several, we use the tuple syntax, in case you're interested. This constraint is always satisfied, so it's not something we see a lot until we get to constraint programming, which we'll cover when we go to type families and constraint kinds. Okay. Let's try the exercises. Fix the following classes by annotating them with kind signatures. JHC will tell you exactly what the problem is, so be sure to try before uncommenting. Well, of course, here we're writing an instance for maybe, which doesn't have kind A, but actually have kind A from type to type, because it's a type constructor. Oh, there's a viewer. Hi. Say hi in chat. And I'm pretty sure this one is right. Yes. I'm gonna ace these exercises, I'm sure. So now we have this other class, which has an instance for either. And then here either is another type constructor, which goes from type to type to type. Because usually we have something like either EA. And I should have no errors here too. Yep. 3. This one takes, again, is a type constructor, takes the first element, second element, third element of the tuple, and returns a tuple. So this should be the right signature. Hey, thanks for joining up. I'm going through some Haskell extensions exercises, which are very interesting. Bring out a lot of cool concepts. Right now I'm doing the KindSignatures one, which is kind of simpler than the first one. The first one was a little tricky. The second chapters are simpler, but oh sure, I can give you a link. Wait a sec. This here is the link. Yeah, I'm on chapter 3 right now. I think it's very interesting. It's very interesting, and especially if you're not super familiar with these more advanced Haskell concepts, it can be a little mind-bending. So, number 4, we need to write an instance for a function, which is still a type constructor that goes from type to type to type. So we have the first function argument, or not. Yes, just one type, 2 types. Takes a type, returns a type. Yeah, well, it's still interesting because what these exercises teach you is that you really can trust the compiler. It's something that I used to do a lot when first starting, especially because I had a JavaScript background. Was like when the compiler was giving me an error, I was trying to fight with it and trying to convince him that I was right and it was wrong. But usually, it's the compiler is right, like 99% of the times. So if you learn how to read the error messages and trust the compiler, your life becomes much easier when writing Haskell or any type language, I guess. It's just that GHC it's really great. So let's see. I'm not very sure about this. Yeah, no, it's wrong. Yeah, I was right. This takes two arguments and returns a type result. Yes, it is. Okay. 5. This is a trick question, right? Because this is a type. So I think this is fine as it is. Yes. Yeah, it's pretty nice. It's pretty nice. Sometimes I have to go back writing JavaScript and PHP. Well, not sometimes, almost daily. And it's awful. It's really awful. I waste hours fixing bugs that the compiler will catch in 3 seconds. Okay, this is trickier. Is it? No. There are no. All the type constructors are saturated. We have either with 2 parameters, maybe as its own parameters. Yeah, never done Ruby. I mean, I've heard nicer things compared to some languages like JavaScript and PHP. So maybe you're having a better life than me. I don't know. Never tried it. So I think we don't need to change the class for this one. Yes. Okay. This instance looks flexible. Well, for sure this one is a constraint. So we probably need to do this. And then maybe we need flexible instance. It's already on. Okay. Well, feel free to ask if you have any question or something that's not clear. Okay. Yeah, this one is a trick question because he didn't explain this, but I already know how it works. So this goes from type to constraint. And now it's gonna be wrong because I don't know how to say it in English. Yeah, it works. So obviously show, it's not just a constraint, but it's a, I think we can call it the constraint constructor. I'm not sure. Anyways, it takes a type and returns a constraint. Oh no. Okay. Okay, this one is trickier. Is it? Or maybe not. So let's see. Functor. I think is something like this. And maybe it's already something like this. Type to type. So I think this one is going to be a constraint. Let's see. I'm not entirely sure about this one. No, okay, works. Yeah, just following the types. It's the best way to write Haskell code. Oh no, what's this? 10, a kind error. Assume 2 out of 3 of these have the correct kind. What should it be? Which part is broken? What's wrong with it? Okay, here the problem is that, let's write it down here. The problem is that monad takes a type constructor and returns a constraint. And we're passing it m, but we're passing it m to eq2, which is just from type to constraint. So this obviously can't happen. We can have both at the same time. And that's why it's complaining. Well, and then obviously we also have show a, which is just a constraint. So I think it's still gonna complain if I do this. Yeah. So I wonder if it'll work if I do something like this. Oh, don't worry. Even if you want to ask really basic questions, just ask. Yeah, sometimes it's a little hard to get to grok all the concepts because there's a lot going on. But once you start getting it, it gets much easier. And it's really a matter of going one step at a time, not trying to tackle all at the same time. So this one obviously has to be a constraint. And then I guess we can change m to n there. I won't complain anymore. So it complains if I leave m here because it's GHC, the compiler, doesn't know if m should be just a type, which is required by Q, or a type constructor, so a function that goes from type to type, which is required by the monad. And then we get an error, but if we change this to a different letter, we don't have an error anymore, because now n can be type constructor, and m is a type, and GHC is happy. Okay, this chapter was pretty straightforward. So this concept I'm going through here, it's it's the kind of stuff that you don't really need to write Haskell daily. I write production Haskell every day. It's part of my job, and I never use these instances. These extensions, except for when I'm using libraries that require them. Like I almost never write code by myself that need these kind of things. And then you can just use libraries that use them, and then if you need them, the compiler will tell you, hey, just enable kind signatures, please. You do it, and the code just works. So it can feel a little overwhelming, but it's not something that you really need to do unless you're writing really advanced Haskell, maybe writing libraries for other people to use, or I don't know, or really want to use them for whatever reason. Okay, so I'll move to chapter 4. So today's module will focus on one of my favorite JHG magic tricks, the data kinds extension. We'll see how and where to use it to enhance GADTs in particular, but there are plenty more cases to follow. Okay, let's see. You're probably not very familiar with GADTs, so this will look a little weird to you, but anyways, now we know about flexible instances, kind signatures, and JDTs. We have a pretty solid base to start talking about data kinds. Recall that all types we define have kind type. So data natural, which is a sum type, which is either a 0 or successor natural as constructors. This is a type with two constructors. 0, which we'll use to represent 0. Yeah, of course. Successor, which we'll use to represent one more than its argument. Another natural number. Let's write everything out. The natural type is kind type, of course. The 0 constructor has type natural. Yes. The successor constructor has type natural to natural. Okay. Successor takes an argument, another natural, and returns us a natural that is one more. Recall also that there are other kinds available to us. Okay, the one we saw in the previous chapter, like 30 seconds ago. The data kinds extension extends the behavior of data constructors. Now, whenever we introduce a data type like natural, we also introduce a new kind called natural. Similarly, we introduce two type constructors. Okay. So 0, which normally has a type natural, becomes this one with quote 0, which is a type, which has kind natural. And successor is a, okay, natural is now a kind. The 0 constructor has kind natural. The successor constructor has kind from natural to natural. Successor is a type of kind natural to natural, as it takes another type of kind natural as an argument. We say that this is a promoted data type, as it now exists at both the value level and the type level. We use the apostrophe, usually called a tick, before the type to distinguish between its value and the type level version. So we have a class natural kind, which takes A, which has kind natural, And then we can write an instance natural kind of the type 0. Which is not a data constructor anymore, but it's a type. And then we can write instances for the data type successor too. Yeah, it's a little mind-bending and confusing. The thing we're mentioning here is that things of kind natural don't have any values. They only exist at the type level. There is no value that has type 0, ticked 0. With that in mind, you might be forgiven for wondering what the point is. The power of data kinds is best demonstrated when we use them for phantom type parameters, which, remember, also don't have a value attached. So for example, we have this data vector, which takes length, which has kind natural. Remember that we can write this because we have kind signatures enabled, and takes a, which has kind type. And then we have vnil, which is a vector of 0 length. And now we have vcons, which takes a vector with length n, and returns a vector with length n plus 1. So I guess this stuff lets us go into dependent types territory. I don't know what I'm talking about. What we have here is a list, as we have seen before, but with a twist. The type of this list, which we'll call a vector, contains the length of the list. Now, why would we want this? Well, recall the magic of the exhaustivity checker when we use GADTs. So head, take a vector which has length n plus 1, v returns a, and this function is total because we are guaranteed that this vector can be empty, because otherwise this one would be 0. So I guess we can try. We can try doing this and see what happens. So if we have a vector of length 0 of a to a, we get an inaccessible pattern match. So that's good. So the compiler is helping us, and that's always a great thing. Okay. We don't have to match on the vnil case because we will never construct a vnil whose length parameter is a successor. There is no need for maybe because it can go wrong at runtime. Let's stop there. Let's do something really clever. Okay, so it writes a function called zip, which takes a vector of length n of element a's, a vector of length n of element b's, and returns a vector of the same length n containing tuples of a's and b's. Now, if you've written zip before, you'll be used to seeing 4 cases on which pattern match: nil nil, const nil, nil const, const const. However, we see that the type that are vector in the type that the vectors are of the same length. By saying that the first one is vnil, the type checker knows the second one must also be the same. Similarly, for the vconst case, the type checker knows that they must be both be vconst, and their tails must be of the same length. Yeah, this is very cool. The type checker can do a lot with this little bit of extra information, and we can express some more powerful concepts. We'll see later on that with some pretty simple extensions, such as type operators. Data kinds is the first step towards an extremely rich type level vocabulary for us to misuse. Nice. I'm pretty sure I will misuse it. Plenty. Okay, let's check the exercises. I'm feeling that this will be a little tricky. Let's see. Okay. One of the restrictions around classes that we occasionally hit is that we can only have one instance for a type. There are, for example, two good candidates for a monoid instance when we think about integer. Yes, both sum and product are correct. Write a new type around integer that lets us choose which instance we want. Write the two monoid instances for integer. Why do we need flexible instances to do this? Okay, let's try. Let's try. Definitely get into trickier territory. New type. Integer tick, which is integer tick integer. Integer or integer? Who cares? Write the two monoid instances for integer. Okay, I'm a little confused now. Yeah, no, I don't think I have to do this. That defeats the point of the chapter. So let's open back this one. Okay, I think we have to use a phantom type. Which could be this one, maybe. Let's try. So now we can write the two instances for integer. It's empty actually. I think Japan was the semi-group method. Integer 0. We are not getting errors, so that's something already. We need flexible instances. Why do we need flexible instances? Because we have a concrete type here, not a type variable. So this forces us to use flexible instances. Does this work? Let's see. Scrabble. I think I have to manually add the extensions here. Do I? Module. Maybe load works. Yeah. Do we have to set distinction manually? Let's try this data kind set xgdts set kind signatures add source let me just check very quickly. Language extensions. This should work. Not sure why it's not working. So I don't get any error here, which feels like it's correct. So I get all the possibilities. Why it's not working? Oh, do I have to do something like this? What if I do this? Oh, hi. Thank you for joining. This is Manjaro Linux. I don't know if I spelled it right. I don't know why it's not working. Well, anyways, I'm pretty sure this is correct. We can try using it. So let's try. Yeah, it works. I have no idea how to enable extensions in the REPL, which is unfortunate, but we got no compiler errors, so this should be correct. Okay, number 2. We can write a type that is of kind type, but has no value level members. We usually call this type void. Okay. If we promote this with data kinds, can we produce any types of kind void? I think not. I don't think we can. Because since this one has no value level members, then we can have no types members. Not entirely sure, honestly. What are the possible type level values of kind may be void? Interesting. That's very interesting. Honestly, I have no idea. So we have maybe, which goes from type to type, because it's a type constructor. When it gets promoted with data kinds, it becomes a kind constructor. So from kind to kind. Then we have void, which has no constructors. And we have the promoted void, which has, I don't know. Wizardstick, if you know what the answer to this is, feel free to write in chat, because I'm very confused now. I'm very, very confused. Why am I getting no errors? Let me try starting Emacs very quickly, because there's something not working here. Uh, 04 exercises. So flight check stopped working, which is not very helpful now that I'm trying to solve these exercises here. Is there like a LSP restart? This is very annoying. Okay, so it seems like Haskell the engine stopped working completely for me. No, sorry. Is it running? It's confusing. Okay, nothing running now. Okay, it's working now. Is it working? It's not. I got an error for a second, then it disappeared. What's happening? I'm sorry, there's something wrong going on with my setup. I'm not entirely sure. I mean, it worked perfectly until chapter 3. And now it stopped working completely. It's not a book. It's a repository. I can paste it again. Wait. Here it is. It's pretty interesting. It's some very nice exercises covering a little more advanced Haskell concepts. So for some reason the type checker here in Emacs stopped working completely for me. Oh, you're welcome. So I'm getting some errors here about mismatching GHC version, but these weren't stopping me before, so why are they stopping me now? Wait, I don't even remember if I have either engine or language server installed right now. Either this is very weird. I think Doom Emacs already does that, doesn't it? No, I was definitely looking for a Haskell hidden engine wrapper. Oops. Okay, it's definitely installed, so I can try setting it up. config. Anyway. Yeah. Okay, let's try this. Oops. Let's change this to here wrapper. Let's see, it works now. Got an error. Why? Because I need to do this. Oh, it works now. Okay, cool. Sorry for the detour. Hopefully we're back on track now. Is it still working? Oh no, I stopped again. I don't believe it. I'm using here wrapper though. Describe variable. P Haskell process path here wrapper. P Haskell process path here wrapper. I'm very annoyed right now. I don't want to be wasting time doing this. So actually I have both here wrapper and here running. So why is it complaining? Can I just do stack install JHC? compiler is installed. I think I know what the issue is. I think I know. I think if this doesn't work, I will stop the stream here because it's not very interesting. Yeah, doesn't work. Oh well, it's a shame. Thank you for watching. At least I work on the other two chapters, and hopefully I will be able to work on the other twos next time.